Hi everyone, my name's Alex and today we're going to talk about electrophilic substitution. First of all, so what is an electrophile? So an electrophile will accept a pair of electrons, so it's usually positively charged and is attracted to areas that have got high electron density. So if we think back to benzene, we know that benzene has got a really stable structure. It's got a ring of delocalized electrons and it won't undergo addition reactions very easily. So to add anything else onto benzene, we need to substitute it. So that ring in benzene it's made of electrons, so it's got a high electron density, and the electrophile, which is positively charged, is attracted to that ring. So that electrophile will accept a pair of electrons from the delocalized ring, and it forms a new covalent bond. So attached to this carbon atom is both the hydrogen and the new electrophile, which is bonded to the benzene. So now obviously this delocalized ring has now lost 2 electrons because it's formed a new covalent bond, so it's very unstable, and this is an unstable intermediate. So to make sure the ring is stable again and the whole molecule is stable, we have to add 2 more electrons back into the ring. So for that we have heterolytic fission of the carbon-hydrogen bond. So the 2 electrons from that bond move back into the ring and release a hydrogen ion. So now the ring has been reformed, our electrophile has been substituted onto the molecule, and we now have the complete reaction plus an extra hydrogen ion. Now don't forget to write the extra hydrogen ion in, because you'll see when we do an exam style question soon that it can be crucial when you're reforming catalysts in nitration of benzene. So let's just go over those steps again. So firstly, the electrophile will accept a pair of electrons from the delocalized ring, and this step is the slowest step in the reaction. It forms a new covalent bond with the carbon, and now the ring is unstable. When you're drawing out this unstable ring, make sure the corners or ends of this U go over there like that. Make sure they come all the way to the 2nd and 5th carbon, otherwise you can lose marks accuracy in an exam. And then just pop a little plus sign in the middle of it. So now you've got your unstable intermediate, we need to reform that ring to make it stable again. So you get heterolytic fission of the carbon-hydrogen bond, and that pair of electrons moves back into the ring and it is now a stable product, and a hydrogen ion is now produced. Right, so now we've looked at the mechanism for electrophilic substitution in benzene, we'll look at an example. So an example that came up in my organic paper was nitration of benzene. Nitration of benzene is substituting an NO2 group for a hydrogen. So first of all we need to produce that NO2 group. So for that we need a sulfuric acid catalyst. So to form that electrophile, the nitro electrophile, which is NO2+, we need to add nitric acid to sulfuric acid. With that we get NO2+, HSO4- and water. We can see that the NO2+ will be our electrophile. So let's just talk through this mechanism again. So the NO2 is the electrophile and will accept a pair of electrons from the delocalized ring in the benzene. And that's the first step, and that's the slowest step. So the second step, now the delocalized ring has been disrupted, it is unstable. So we need to reform that ring, so there is heterolytic fission of the carbon-hydrogen bond, and that pair of electrons moves back into the ring and it is now stable. So from that you've got your nitrobenzene, which is the new substituted product, and you've got a hydrogen ion. Now if we look back at the reaction for generating the electrophile, which was the NO2+, we didn't regenerate that catalyst. Now as we know, catalysts can't be used up, or they must be regenerated at the end of a reaction. So we need to regenerate that catalyst, which is the sulfuric acid. So all we do is that hydrogen ion, which was expelled from the benzene during the substitution, reacts with the HSO4-, which will regenerate our sulfuric acid catalyst. There's a few conditions you need to know for this if you're carrying it out practically. So it needs to be carried out at 50 degrees C and under reflux, and both the nitric acid and the sulfuric acid need to be concentrated. So the second example we're going to talk about is halogenation of benzene. So if we remember back to electrophilic addition, the double bond is an area of high electron density, and it can induce a dipole and cause an electrophile to form from the halogen molecule. Because the delocalized ring in benzene hasn't got a high enough electron density, it can't induce that dipole as well, and it won't produce an electrophile. To produce the electrophile, we need to use a halogen carrier catalyst. Now, the halogen carrier catalyst will either be the iron halide or an aluminium halide. Now, what these do is they generate the electrophile by accepting one of the atoms from the halide molecule. So you have, for example, a Br plus and then a FeBr4-. So the rest of the mechanism is pretty much the same. It's just the standard electrophilic substitution mechanism, where you've got the electrophile, so in this case it's the halide ion, or the, for example, Br plus ion accepts a pair of electrons from the delocalized ring. There's then a heterolytic fission of the carbon-hydrogen bond, and the pair of electrons moves back into the ring to re-stabilise that ring again. But again, you'll notice our catalyst, which is a halogen carrier catalyst, hasn't been regenerated. So to regenerate that, we just take the extra hydrogen ion and it reacts with the, for example, FeBr4- and to produce the hydrogen bromide and regenerate that catalyst.